Hello everyone, my name is Engineer Tina Chemeka. Today we're going to be looking at engineering analysis and concept control, MEC 806. By the end of the class, we should understand the concept of engineering analysis and control. Basically, from the slide you're going to be seeing, it says that engineering analysis involves the use of mathematical and computational tools to describe, evaluate, and predict the performance of engineering systems. So when you look about describe, explaining how systems function. Evaluation talks about comparing that system with the standard, you understand? And predicting means forecasting what would happen. So an engineering analysis helps us understand the concept of describing the system, evaluating it, and predicting either the functions or predicting the behavior of a system. For example, when you have a production line and you want to forecast the possible time there will be downtime or when there will be need for maintenance, with the use of engineering analysis, one can actually tell that after several periods that there will be need for maintenance. When you talk about engineering analysis, it's basically to use mathematical and computational tools to describe, evaluate, and predict the performance of an engineering systems. It says transform physical systems into mathematical models that can be analyzed to determine parameters such as displacement, velocities, stress, temperature. So it transforms systems into mathematical models. When you talk about systems, talking about the operation of a particular activity or a series of activity or the behavior of a system. For example, the production line of a production firm, or human behavior, or the behavior of a certain system into numbers. What are the key steps in engineering analysis? One, it says problem definition. The very first step of engineering analysis is what? Problem definition. So you have to define, you have to understand the engineering scenarios, identify input and output functions, understand what exactly happens into the system. What are the variables of this very system? For example, if you're talking about analyzing maybe a production plant or analyzing a system, you have to understand the input to that system and the possible output. So the second step in engineering analysis is system modeling. So the moment you understand the input variables, you understand the output variables and the constraint, you now develop a model. You now develop a mathematical model representing these systems, because we can't carry these machines into the computer. You understand? Rather, we represent these the systems itself with certain box or parameters in our computer systems. You understand? So and that's where we make use of certain analysis tools such as the Simulink, MATLAB, Python, to be able to analyze the behavior of certain systems and building blocks that will represent each step of that system. So the second thing is then the analysis, you understand? So under the analysis, we apply analytical and numerical methods to obtain system response. So having built a system model, you have to analyze it, based on the model you built. The analysis involves both mathematical analysis, both statistical analysis. These are various analysis that ensures that this system, these are various tools used to checkmate how the systems behave. Then once you're done with the analysis, there is a point for validation. Validation means comparing this analytical result with experimental or real-time data. So one of the mistakes we make over time is that we as researchers or we as students, we always come up with researches which might not really suit the real world experience. So validation actually ensures that these systems that we've built, or this model, this analysis, these our values, or this hypothesis we've actually generated, how does it really align with the real world experience? Think about someone who wants to model the behavior of solar panels in a particular community. So he's doing this modeling and this analysis with a system, either by using a PV-SYST. So having gotten certain kind of values, it is very essential to compare these values with a real life solar panels. You're able to generate, from your analysis, you were able to discover that a particular solar panel can generate about about 250 amps of current, and whatever parameter you want to compare it with. But in real life, you have to bring that solar panel, try to expose it to the sun and know whether it will give you equivalent, to that equivalent of that power that was mentioned. So that is what we call validation. Then the next thing we have to talk about, the next step is optimization. You've discovered the behavior of the system. You've modeled the system, analyzed it, validated it. Now you have seen the flaws. Maybe after comparing the system with the real world experience, you find out that there is a need for an adjustment, and that adjustment to achieve a desired result is called optimization. So optimization basically talks about adjusting design parameters to improve the performance, So the concept of that solar systems, maybe in the course of your design, you build certain kind of systems, you have different kind of battery types. So in order to optimize the system, you need to adjust your design to, get the desired results. So in order to understand engineering analysis, it's very important that we understand various kind of systems. The first type of system is the linear system. The linear system refers to a system that behavior that obeys the superposition principle, like the mass spring damper systems or small displacement. So the linear kind of systems are systems that work with a basic principle. We know that the moment you increase the mass of a body, the moment you increase the mass of a body on a spring, there will be displacement. You understand? It's a linear, action. So as you're increasing this parameter, the corresponding parameter increases. So we have the nonlinear systems. So the nonlinear systems, output is not directly proportional to the input. These are engineering systems in which the increments in the input does not really connote the increase or displacement of a particular kind of parameter. You understand? These are non-linear system. Example is the pendulum at a large angle. You understand? So we have the deterministic systems. A dynamic system is a system whose response is predictable given known input. So that's the name. Deterministic talks about a system that has a response that can be predictable. So common example is the DC motors under constant voltage. You understand? We have the stochastic systems. The stochastic systems contains random or uncertain components. Example is the wind energy system, like the stock price. These are systems that are very uncertain. When you're doing modeling, there are certain kind of systems that you can't, comfortably rely on the values due to the nature of their variability. There are times they can change. They might be up today, they might be down today, just like the wind speed. So the wind can be high today, it can be low tomorrow. So it's an example of a stochastic kind of system. Then we have the continuous systems. Variables change continuously with time. You understand? Electric circuits, for example. So you see that a continuous system is actually any kind of system that its variable keeps changing. I was telling someone about a particular kind of chemical that has a changing behavior at different temperature, or the longer it stays. For example, let's talk about fermentation. The more alcohol stays, the more the behavior changes. You understand? So we have the discrete system. The discrete system, variable changes at specific interval. In a discrete system, the changing of that variable is actually at an interval. It's timely. So at every 2 minutes there's a change. These are discrete system. It is very essential that you understand this type of systems before you talk about modeling. Now, why are we talking about the systems and modeling? Because as a researcher, as a master student, in the end of your program, you are meant to come up with a research, and this research entails modeling. And if you don't understand the behavior of systems, you might not be able to model very well. So on the other hand, let's talk about control. So control system actually are designed to regulate and manipulate the system behavior. So we've talked about various kind of system, but the concept of control are facilities built or system built or ideology built in order to control the behavior of a system, just like its name entails. Control refers to a way in which engineers can control this behavior. Then there are two types of control systems. One, the open loop control, no feedback. So this open loop control refers to a kind of control in which there is no feedback, in which there is no return of information. For example, an electric kettle. An electric kettle, when you're using an electric kettle, once the water boils, it gives signal, tells you that this water is boiling. It starts whistling. It doesn't stop the water from boiling. The boiling might continue. So then a closed loop refers to a system that sends feedback to the system itself. You understand? So talking about a closed loop in the context of an electric kettle, if there is a closed loop in an electric kettle, it means that, for example, if the water gets boiled, the system would either turn itself off. So it will send a signal to the system that, oh, this water has actually boiled. Then let the system shut down. That's actually a closed loop. Does not need human interference. You understand? So it's also seen in things like our air conditioned thermostat and thereabouts, where every control system would have a controller. And what the controller does is to determine corrective actions. You understand? Corrective actions are the system that actually informs a part of the control system that tells the system that something has changed. You understand? So it has an actuator. And basically what an actuator does is to, execute an action, to execute a controlled action. Basically, you understand? Just like this. So we have the sensor that measures that output function. You know what the sensor does? So sensor measures a physical activity. You understand? Either by sensing temperature, sensing the behavior, sensing vibration. So we have the processing plant. That's the system itself. So that is the brain of the control systems. That's where information gets into. You understand? So within the confines of this course, we're going to be looking at first order differential equation and dimension analysis, because this is the basic of engineering analysis and control. So then, what are the importance of engineering analysis and control? One, it enhances system performance and reliability. Yes. So the essence of engineering control is to enhance what? The performance of a system, by having modeled it and understand the behavior, you can actually, you can optimize it, you can enhance it and make it more reliable. Two, it enables predictive maintenance and optimization. Yes. So when you've modeled a system, let's assume that you've modeled a plant or a machine, you understand how long it needs to work before this machine can break down. So understanding the behavior, you can say, if this machine works for 200 hours, it will most likely break down. So you have actually built a model. So you say if so amount of input is actually being put into the system and it produces so amount of output, it's time for maintenance. Just the way some of us actually say, if you drive your car for like 3 kilometers, you want to change the oil. That is it. So it helps us predict what? Maintenance and optimization. 3, it reduces design and operational costs. Yes. So when you understand the behavior of a system, you're not doing trial and error. You understand? You've modeled the system and you know the parameter that gives optimal result. You go straight for it, other than building systems that you build and then know whether it will work or not. Then the fourth one is support automation and intelligent systems. Yes, there are no intelligent system automation where the concept of control, engineering analysis and control systems. This system read the behavior of the environment. These systems are actually guided by models that ensure that they function effectively. So let's talk about modeling of engineering systems. So the term modeling is the process of creating a simplified representation of a real system that captures its essential characteristics. It bridges the gap between theoretical analysis and practical implementation. That's the concept of what? Modeling. So there are types of modeling. 1, physical models. 2, mathematical models, and 3, simulation models. A physical model refers to, the scale experimental prototype. Maybe you want to create a prototype of a particular kind of machine to see how it will behave. That's actually a physical model. So we have mathematical models. Mathematical models refer to equations of a system behavior. So when you have studied the behavior of a particular machine or a particular system over time, you come up with an equation. That's the mathematical model. Let's talk about the simulation. That's the third one. Simulation models. So simulation models are computer-based models that represent the testing of that controlled system. The word simulation refers to you carrying out a physical activity in a virtual way. You understand? So these are the 3 types of model. There are various kind of models. That's your mathematical models, ranging from your Newton's second law, your Kirchhoff law, your Fourier law of heat conduction, your Bernoulli's equation. These are all linear model. There are 3 ways of determining model. The first way is least square estimation, 2, correlation analysis, and frequent response testing. So these are 3 ways. Correlation analysis talk about the comparison between a physical parameter and a virtual parameter, like comparing that physical feature against what you've done with your model. Then the frequency response refers to your normal statistics, where you talk about the and over and thereabout. So the next one we're going to talk about is linearization of non-linear systems. Many real-world systems actually are non-linear, you understand? So but you as an engineer, you have to build a model that make it function as a linear system. Then model validation. How do you achieve model validation? So validation ensures that the model accurately represents reality. What are the techniques involved in validating a model? 1, comparing simulation results with experimental data. 2, performing sensitivity analysis. 3, adjusting parameters for best fit. So the first one talk about the comparison of that simulation results with the experimental data. Then 2, performing sensitivity analysis and adjusting parameter for what? For best fit. These are various ways of model validation. So, in summary, the concept of engineering analysis helps a postgraduate student, understand how a model is being built, how they can go about developing a model, and how various systems function in order to understand the best way to model those systems. I'll be attaching some assignments, or you can feel free to drop a question under the comment section.